Hello, students. Um, Good morning. We are going to see the greedy technique, wherein you will be seeing. You have already seen the Prim's algorithm, Kruskal's algorithm, where it is used for the minimum cost spanning tree. So the next is the single source shortest path problem, wherein you call something called as Dijkstra's algorithm is used. So here, when you say it as a single source shortest path problem, you will be given with a weighted connected graph. Okay, you need to find out the path. In the dynamic programming, we have seen that we have used the Floyd's algorithm. What is Floyd's algorithm? It is all pair shortest path problem. Okay, it is for all the vertices. So all vertices will be considered as the source. Simultaneously, all will be the destination too. But here, when you see the graph, you will come to know that you will be taking any one of the vertex as the source vertex. So from the source vertex, it will be moving on to all the other vertices. So the Dijkstra's algorithm, it is more or less similar to a Prim's minimum cost spanning tree algorithm, where the labeling will be done or it will be found out. Each path when you take, the computation will be different from the Prim's algorithm. But we go follow the Prim step, where in Prim step we have seen that whenever you take a spanning tree construction, you will be starting with the arbitrary vertex. You will be moving on to the next vertex, which is unseen. Okay, which will be added to the tree vertex based on the nearest adjacent. All there will be so many adjacent vertices, but you will be going with the nearest adjacent. If at all there is a tie, the tie will be broken arbitrarily. So here also we follow the same thing. So among the vertices which is not already in the tree, you will be finding a shortest path, where we will be using the formula as, if you consider the vertex as V and the next vertex to be going to be joined as U, then you will be saying it as dv plus w of v comma u, where w of v comma u says what is the weight of the edge v to u. dv is from the source vertex, what is the edge cost of the source vertex to the current vertex. So that is nothing but dv plus w of v comma u. So now we are going to see a graph, where in graph you will be calculating all the vertices. So here, when you say it as Dijkstra's algorithm, what we do is, in Dijkstra's algorithm, it will be going for a shortest path to a graph's vertex in order to find the distance from a given source. So first it will be finding the shortest path from the source to a vertex nearest to it. Then you will be going for the second nearest, and you will be going on like that. So in general, what we do is, before the ith iteration commences, the algorithm has already identified all the I minus 1 vertices from nearest to the source vertex. So this can form a subtree, and the next vertex chosen should be vertices adjacent to the vertices of tree TA, which is considered as called as the fringe vertex. So to identify the nearest vertex, what it should do is, it should compute the every smallest vertex, and it will be going near to it. So here, when you say it as the Dijkstra's algorithm, you are going to find out the nearest vertex. So for this, we will show, I'll show you an example, then we will be moving ahead with the thing. So here you are given with the Dijkstra's algorithm, which is called as a single source or path algorithm. So in Dijkstra's algorithm, what we do, we will be considering only a single source. So you are given with a graph. Among the graph, we are considering one vertex as the source vertex, which is vertex A. From A, we will be moving on to B, C, D, E, etc. So A will act as the source vertex, and from that we have to see. So among this, which is the nearest adjacent vertex of A? The nearest adjacent vertex of A is D. So now we will see how to solve it. So you are going to take vertex A, and you will be seeing what is the adjacency. A to B it is not there, A to C it is not there. So see the direction also. So B to A is there, A to B is not there. So A doesn't have an adjacent vertex. So similarly for C and E also. So for A to B it is infinity, infinity, E also infinity, A to D the value is given as 7. So we will take that value 7 for A. Okay. So now when you say this, we are considering it as A as the source vertex, and you will be going with the next adjacent vertex as D. So now you take D, from D it is adjacent to B, but you are not going for directly from A to D to B. You will be seeing it as it is adjacent to that is D acts as the intermediate vertex. D acts as the intermediate vertex for B. So the value is 2. So already A to D it is 7. So 7 plus 2 it is equal to, we will be taking it as 9. Now for C similarly, you see for C also it is already 7. 7 to 5 it is 7 plus 5 it is 12. So from D it is adjacent to C, which is having the value as, now E it is 7 plus 4 it is equal to 11. 11 from D. Okay. So among this 3, which is the shortest? The shortest is uh, to B with the value as 9. So the next nearest is B. So A to D plus D to B, it is 9. So now we can take A to B, B to C also. So it is 9, 9 plus 4, it is 13. So from B it is adjacent to C, whose value is 9 plus 4, which is equal to 13. So 12 or 13, which is nearest for C? 12 is nearest. So we go with 12 only. Okay. Here B is acting as the intermediate vertex. Now for B to E, it is not. So it is, we will take infinity and 11. So infinity is the next. So it is 11, comma D. So among these two, which is nearest? Nearest is D to E with the value 11. So we will take that. E is the next adjacent. So we are taking it as 11, comma D, where E is adjacent to D. D is acting as the intermediate vertex. So now 12 and D. So which is the C. C is nothing but 12, comma D. So from this, what you can understand? It says that A is the source vertex. So you'll be stating with A to D with a value as 7. Now you are going for a B whose value is equal to 9. Then you are going to E whose value is equal to 11. Then A to C whose value is equal to 12. So this is how you find out all the A acts as the source and all the remaining vertices becomes the destination. Okay, clear? So this is how we are going to find out the Dijkstra's algorithm, which is a single source shortest path problem. So finding the next vertex, which is becoming the simple task for finding a vertex with the smallest d value. If there are ties, ties can be broken arbitrarily. So after we are identifying a vertex U star, which is added to be the tree, you need to find out two operations. One is moving U star from the fringe up to the set of the tree vertices. For each and every remaining vertex U that is connected to U star, you will be identifying what is the weight. So weight is nothing but W of U star comma U in such a way that your D U star plus W of U star comma U should be less than DU. Now you are going to update the labels as well as the distance. Label is what? From U we are moved to. For example, D is the next shortest vertex. We will be taking D as U star. What is the distance? Through A to B is 15. A to B plus B to D is Less means you will be going with the less value. So the corresponding value will also be updated. So now when you go for the Dijkstra's algorithm, this is the algorithm given, a weighted connected graph G, which is having a set of vertices and edges, and it's also given with the source vertex. Now you are finding the length dv of a shortest path from S to V, and its penultimate vertex also has to be identified. So you are initializing the vertex Q. Now initialize vertex priority Q to empty for every vertex V in V. So every vertex V in VE, what you will be doing is you will be saying it as dV is infinity. Distance of the vertex is infinity. What is the penultimate vertex? It will be null. So now you are going to insert the vertex priority into the priority queue. So just into the queue, Q is Q, where you will be going with the vertex and its distance value. So now your ds is 0 and you are decreasing, updating the priority of S with the ds. So decreasing your Q by 1, which is your vertex S comma ds. Now what is the tree vertices? Tree vertices is null. So how many times you need to do it? We have already seen in the spanning tree that if there are n vertices, you will be having n minus 1 edges for the spanning tree. Similarly, here also, if a vertex is considered as the source, remaining all the vertices will be considered as the destination. So the loop has to be repeated n minus 1 time. That is nothing but v minus 1 time. So you are going to delete the minimum priority element from the queue. So u star is nothing but whichever is being deleted based on the priority. Now you are using the union operation. Union operation is nothing but vt union u star, where you will be uniting the tree vertex, whichever vertex you have taken. So for every vertex you have chosen, vertex u in v minus v, that is adjacent to u star, what you are going to do is you are checking whether your distance of is lesser. So whatever distance which you are going to take is less, then you have to update it. So I update the penultimate vertex and the distance, and you are decreasing the queue length by 1 by reducing it from the vertex u and du. So now based on this algorithm, we will solve a problem. So what is the problem? The problem here given is you are having a graph. From the graph, we like the Prim's spanning tree. What we are going to have is you will be having 3 columns, which will be saying the tree vertices, remaining vertices, and the illustration. So what is the tree vertex? Tree vertex is the source vertex. A is taken and it is initially it is 0. Now we will be considering what are the vertices which are adjacent. See here, if you see B is nearest adjacent to A with the value 3. C is not adjacent to A, so the value is infinity. D is adjacent to A, whose value is 7. E is not adjacent to A, so its value is infinity. So among these two, 3 and 7, which is minimum? 3 is minimum. So we have taken it as B is adjacent to A with the value 3. So that has been taken here. Now, B can act as the intermediate vertex. So from A, you don't have a direct edge to C, or D also there is an edge, but the value is 7. So you are now seeing by acting B as the intermediate vertex, keeping B as the intermediate vertex, are you getting a shortest value? So if you keep B as the intermediate vertex, what is the value? A to B is 3 and B to D is 2. Among 3 plus 2 is 5. So 5 is minimum or 7 is minimum? 5 is minimum. So you are saying it as for vertex D, you are saying that it is going with a minimum value. What is the minimum value? B is acting as the intermediate vertex and you are saying it as D of B comma 3 plus 2. That is nothing but 5. Among 7 and 5, 5 is minimum, so you are considering that. Now, A to C, there was no intermediate, no edge, so the value was infinity in the previous step. See here, you can say that it is infinity. But now when B is acting as the intermediate vertex, you will be saying it as C of B comma 3 plus 4. So when you say it as B plus 4, what will be the value? The value is nothing but you are saying it as A to B it is 3 plus B to C it is 4. So C of B comma 3 plus 4 is, you are saying that it is 7. Understood? So infinity and 7, 7 is minimum. So we are considering that. But whether B to E there is an edge? No. So it is still infinity only. So here we can say that it is infinity. So among 7 and 5, which is minimum, 5 is minimum. So the next vertex which you have chosen is, it is nothing but you are saying it as D. So now you see whether D can act as an intermediate vertex. So now when you say it as A to D, don't take it as 7. It is A to D is now 5 through B. So what will be the value? The value is nothing but you are saying that A to B, what is the value? It is 3. B to E, it is nothing is there. But A to B, B to D is 5. So D to E is 4. So we are saying it as E of D comma 5 plus 4. Whereas for C, it is still it is, when you, if you consider D as the intermediate vertex, it becomes 5 plus 5, 10. But already we have a lesser value, that is 3 plus 4, 7. So we are considering that only. So now among these two, which is the intermediate? The intermediate is and the shortest one is C. C of B comma 7. So the next is C of D comma 9. Okay. So now when you say it as the paths, what are the paths you have? You have from A is our source vertex. So you have from A to A to B, whose value is equal to 3. That is the shortest one. A to B, it is 3. Now, A next is you are considering A to D. So, what is A to D? A to D is nothing but it is 3 plus 2. 3 plus 2, you are having it as, you are having it as 5. Next, what is A to C? The next one which is taken is A to C. So what is A to C? A to C is, you are taking it as 3 plus 4. What is 3 plus 4? It is nothing but it is 7. Now, finally E. What is A to D? A to E? A to E is nothing but you are taking A as the source vertex and E as the destination. When you take A to E, whose values will be equal to 9. So here you can see it is slowly getting increased. A to B, if you see, the value is 3. A to B, it is 3. A to D, it is 5. A to C, it is 7. A to E, it is 9. So A is the source vertex, B, D, C, and E are the destination. So totally how many vertices are there? There are 5 vertices. So if one is acting as the source, how many paths you will be getting? You will be getting a maximum of 4 paths. Suppose in some cases, if there is no edge, here we have taken a undirected graph. If suppose if it is a directed graph and if there doesn't exist any edge between A to E through any of these vertices, then we will be considering it as only 3 paths. So based on the number of edges which is connected to the graph, we can say that it is nothing but it, here in this case we have got 4 paths. So how many vertices are there? There are 5 vertices. So 5 minus 1 is nothing but it is equal to 4 paths you are having it at a maximum. So this is what your Dijkstra's algorithm says. It is the single source, all the source vertex, and here you can see you have the destinations. So all the other vertices act as the destination vertices. So this is how you need to find out the Dijkstra's algorithm for the uh, single source shortest path problem. Please don't confuse it with all pair shortest path problem. Means it is a Floyd's algorithm where you will be using the dynamic programming method. Single source shortest path means you will be saying that it is the Dijkstra's algorithm and you will be using the greedy technique. Understood? Clear? So here we are going for the Dijkstra's algorithm where you will be using, see here there is, this step says that for I equal to 1 to v minus 1, that's what we have got. There are 5 vertices, so we have gone through 4 stages, and after 4th stage we will be finding the 4 different paths. So it doesn't work within the negative weights, but it is applicable for both the directed as well as undirected graph. Now if the graph is going to be represented as an adjacency matrix, it will be represented as b squared. If it is going to be represented as a linked list, you will be having it as order of e into log v. So this is all about your Dijkstra's algorithm. So Dijkstra's algorithm is nothing but finding the single source shortest path. Okay, so this is how the problem is. This is how the algorithm works. So thank you all.